Hello everyone and welcome back. I'm going to get started here momentarily. Okay. This is again a recap of last week's homework or last session's homework problem. And this is FoodMax milk example. Once again, we'll be moving relatively quickly, only because I want to maximize the time you have to work on the homework problems daily. And also you should be getting quite comfortable at this point with being able to solve these or to translate these problems from natural language into mathematical language, as long as there are no curveballs thrown at you. In this question, we will have one small curveball, so we'll talk about that when we get to it. So this is the FoodMax milk example. The FoodMax milk grocery store sells 3 brands of milk in half gallons. Its own brand, a local dairy brand, and a national brand. The profit from its own brand is 97 cents per carton. The profit from the local dairy brand is 83 cents per carton, and the profit from the national brand is 69 cents per carton. The total refrigerated shelf space allotted to half-gallon cartons of milk is 36 square feet per week. A half-gallon carton takes up to 16 square inches of shelf space. The store manager knows that each week the store sells more of the national brand than the local dairy brand and its own brand combined. In addition, the local dairy brand can only supply up to 10 dozen cartons of milk per week. The store manager wants to determine how many half gallons of each brand to stock in order to maximize profit. So what we're going to do is we're going to look at my already completed equation and then refer back to this while we discuss what the numbers mean. So we have max z equals 0.97x1 plus 0.83x2 plus 0.69x3. Those are the profit per item. And we see that in the first couple paragraphs. 97 cents a carton, 83 cents a carton, 69 cents a carton. This information is subject to, and these are our 3 constraints. The first one is interesting. 0.11x1 plus 0.11x2 plus 0.11x3 is less than or equal to 36. I got that number because a half-gallon carton takes up to 16 square inches. 16 square inches is 0.11 square feet. So what I've done, we have square inches and square feet, so we have to convert them both to the same unit of measurement. I did that by changing square feet into changing square inches into 0.11 square feet. Next, we have x3 is greater than or equal to x1 plus x2. We see at the end, or near the end, the store manager knows that each week the store sells more of the national brand x3 than the local dairy brand and its own brand combined. So x3 is greater than x1 and x2. That's what we see here. But x3 greater than or equal to x1 plus x2 doesn't work when we're using the computer programs. So we have to change it so that we have only an integer value on the right-hand side. I do that here. x3 is greater than or equal to x1 plus x2 changes to x3 minus x1 minus x2 is greater than or equal to 0. This is something we can work with in QM in Excel. So, moving on. Our third is x2 is greater than or equal to 120. Less than or equal to 120. And we get that because the local dairy brand x2 can only supply up to 10 dozen cartons of milk per week. That's what we've seen so far. This information now allows us from here to then enter into our computer programs to attempt to determine the correct answer. So let's do that now together. The first one is, as always, QM. So module, linear programming, open a new file, and we're going to title it the milk example. We know that we have 3 constraints, as we saw here, 1, 2, and 3. And we also have 3 variables: the store brand, the local brand, and the national brand of milk. And in this situation, we're trying to maximize our profit. So we click OK. Now, just for simplicity's sake, we'll lengthen each of these. And we're going to relabel all of our columns. So the first one is store brand, local brand, national brand. We're trying to maximize, so here we look at our objective function, 0.98, 0.83, 0.69, not 0.97, 0.83, 0.69. Now our constraints we can change again. So look, constraint number 1, constraint number 2, and constraint number 3. The first one is display space. The second constraint is sales ratio. And the third constraint is supply local brand. And once everything has been done like this, it becomes a relatively easy problem to solve. All we have to do now is enter the relevant data in the relevant squares. So display space, each one is 0.11. And we have a total of 36 feet available, square feet available. Our sales ratio. Now we see here, it's x3 minus x1 minus x2 is greater than or equal to 0. This is very easy to input, and we do it like this. 1 because it's positive, minus 1 because it's negative, and minus 1 because it's negative. And it has to be less than or equal to 0. That is greater than or equal to 0. So that's why we change it now. And the last one, local brand is right here. 1 must be less than or equal to 120. Once all of this information has been inputted, very simply, once all of this information has been entered, very simply, we're going to look at this information. But I've made one small mistake, and it was an easy mistake to make. If we check here, we see x3 minus x1 minus x2. What I did was I made x1 positive instead of x3. So that's a mistake. We're going to go into QM, and we'll change that right here. This is minus 1, and the national brand is 1. So the key is that they align here. So once this information's been taken care of, we hit solve, and this is what we get. We see that our solution involves an even split of the national brand and the store brand. And this makes sense because we know that the store brand is more popular, but between the store and the local, the national brand is more popular, but between the store and the local, the store brand is infinitely more profitable. So we probably don't want to carry any of the local brand. This gives us a profit of 271.64 cents. So I'm going to save this problem. And I can close this now. All right, now we go into Microsoft Excel. Okay, so what we're going to do now is we're going to go into Excel and solve it again. However, this time what I've done is I've worked out in advance all of the key cells in Excel. The reason I've done that is because I want to show you that it's not the labels that are important. As long as everything is attached to the proper place, as long as the formulas are set up correctly, what we will get is a situation where even when looking at the spreadsheet, seemingly nothing makes sense. If everything's been entered correctly and the data solver add-in has been used correctly, we still get the same answer. So let's look at our formula now. Let's look at our spreadsheet now. And what we see is essentially an unlabeled spreadsheet. Nothing has really been entered. What I did was, knowing where everything should theoretically go, I entered all of the key information without any of the headings. One of the reasons I'm showing you this is because I want you to see that it is headings that are critically important. Not to solve the problem, but to make the problem understandable for everybody. If I'm looking at this and I have no idea what we're talking about, it would be very difficult for me to understand what's happening here. If we click the solver button over here, and all of the information, as I've already done, has been entered correctly, and we hit solve, we see that all constraints are optimized, and we do get the exact same information that QM provided for us, but it's much less useful in this format. So without changing anything, we'll add a few brief topic headings. So the milk example, these are our products here. And this is our profit. These are our constraints. This is space. This is popularity. And this is supply 2. Over here, this is our usage and the max available. Greater than or equal to, less than or equal to, greater than or equal to, less than or equal to. And again, products and profit. When we add these basic ideas in, it doesn't take very long, but it makes our spreadsheet infinitely easier to read. So that is one reason why I urge you to continue using all of the information I've given you. I'm urging you to continue putting in or adding the labels, even if you don't see how it's immediately necessary. Because when we do have these labels, everything becomes much easier to see. And if you were ever presenting, it would be a much easier situation to navigate. So I'm going to save this. And we're going to close this. And we're going to look at the second example today. This is the Exeter mine example. Exeter Mines produces iron ore at 4 different mines. However, the ores extracted are different in iron content. Mine 1 produces magnetite ore, which has a 70% iron content. Mine 2 produces limonite ore, which has a 60% iron content. Mine 3 produces pyrite ore, which has a 50% iron content. And Mine 4 produces taconite ore, which has only a 30% iron content. Exeter has 3 customers that produce steel: Armco, Best, and Corcom. Armco needs 400 tons of pure 100% iron. Best requires 250 tons of pure iron, and Corcom requires 290 tons. It costs $37 to extract and process 1 ton of magnetite ore at Mine 1, $46 to extract and process 1 ton of limonite ore at Mine 2, $50 per ton of pyrite ore at Mine 3, and $42 per ton of taconite ore at Mine 4. The company wants to know how much ore to produce at each mine in order to minimize costs and meet the customer's demands for pure 100% iron. This question is not overly challenging if we understand what is being asked. So let's look at our equation formulation and then refer back to this page when necessary. We see it's min z equals 37x1 plus 46x2 plus 50x3 plus 42x4. That is very simply the information given to us at the bottom, which is our profit per item. However, the next one, 0.70x1, our constraint number 1, plus 0.0x2 plus 0.5x3 plus 0.3x4, greater than or equal to 400. This is where, and it's identical for each of the next 3 constraints, what we are doing is taking the amount of ore given to us for each, and then adding them together, we have to get to what is required of us at each point. So for the first one, we have all of these, and we have to be at 400 for Armco. The next one, for Best, we have to be at 200. And we're adding these fractions together because that will give us 100% pure ore when it's extracted to the level that it's required, 400, 250, and 290. So once we do this, we can enter all of this information into our QM and Excel programs to determine the correct answer. So let's go to QM first. One more time, we hit close, module, linear programming, and we'll open a new file. We'll call this our Exeter mining example. We have 3 constraints and 3 variables. We're trying to maximize profit. We hit OK. We're trying to minimize costs. That's my mistake. So we're trying to minimize, and we hit OK. Mine 1. Mine 2. Oh, one mistake we had. We're going to open a new file because we have 4 variables in this situation, not 3. My mistake, and we're trying to minimize again. So it's the Exeter mine example. We hit OK. So we'll lengthen these, and then we'll begin altering our headings. Mine 1, mine 2, mine 3, and mine 4. Our costs, we check here, 37, 46, 50, 42. And 42. Constraint number 1 is Armco requirements. Number 2 is Best requirements. And number 3, Corcom requirements. So Armco, each of these now is identical, 0.7, 0.6, 0.5, 0.3. 0.7, 0.6, 0.5, 0.3. Must be greater than or equal to the 400 tons they require. Again, 0.7, 0.6, 0.5, 0.3 must be greater than or equal to the 250 tons they require. 0.7, 0.6, 0.5, 0.3 must be greater than or equal to the 290 tons they require. All of these once completed. Now all we have to do is hit solve. We've seen how easy it is. And what we are seeing is mine number 1. Because it is the cheapest to extract at $37, it's not only the cheapest to extract at 37, it's the highest concentration of ore. So very simply, the smartest choice, if there are no limitations on how much we can take from the first mine, that is the correct choice. We should only mine the first mine. It's the cheapest to mine and the highest concentration of iron. We have to mine at 571.43 tons, and that will give us enough ore to satisfy each of these requirements, costing us $21,142.86. All of the other mines we can see right away are inferior. They're more expensive and they have lower quality ore. So of course we're not going to mine those. So we'll save this as our Exeter example. And we'll close this program. We open our Excel file. And one more time, we'll go through it. Exeter mining example. And again, we will label this time because of simplicity. Products, we'll call it mines in this situation. Mine 1, mine 2, mine 3, mine 4, and our costs, 37, 46, 50, 42. And now our constraints down here, we have 0.70, 0.60, 0.50, 0.30, and each of these we can fill down because we know it's identical in this situation. Constraints should be here. The first one is Armco requirements, best required, Corecom required. Now we come over here. This will be our usage section and requirements. 400, 250, and 290. Greater than or equal to, greater than or equal to, greater than or equal to. We can't enter that because we first have to come down here and we have to do our mines one more time. Mine 1, mine 2, mine 3, and mine 4. Our ultimate goal is minimizing total costs. So total costs we can get from our costs of mine 1 times the amount of time we mine 1 plus our cost of mine 2 times the amount of time we mine 2 plus the cost of mine 3 times what we have to get for mine 3 and plus our cost at mine 4 times the amount of time we mine 4. There's 8 because we have 4 different decision variables this time. One more time, we enter 0.7 times the amount of time we mine 1 plus 0.6 times the amount of time we mine 2 plus 0.5 times the amount of time we mine 3 plus 0.3 times the amount of time we mine 4. We repeat that again. 0.7 times mine 1, 0.6 times mine 2, plus 0.5 times mine 3, plus 0.3 times mine 4. And the last and final time, mine 1, 0.7 times mine 1, plus 0.6 times mine 2, plus 0.5 times mine 3, plus 0.3 times mine 4. Enter. So all our relevant formulas have been entered. Our spreadsheet has been formatted correctly. We click on data and we go over to the solver. Our ultimate goal is found in B17. We're trying to minimize costs. This time we're running computations of not 1 or 2, but 4 cells. We have to add some constraints in. Our usage here must be greater than or equal to H6 400. Usage must be greater than or equal to H7. And our usage must be greater than or equal to H8. Simplex LP, and we hit solve. Once again, we have identical numbers. The problem is satisfied. Constraints and optimality conditions are satisfied. We hit OK. We're mining mine 1 for 571 hours, which will give us enough to satisfy all of our constraints. And it will give us total costs of $21,142.85. Thank you everyone for watching. I'm going to put your homework question on now. Please do your best to solve this problem. I will address you at the 40-minute mark again. All right, everyone. Please be careful with this question. There's a couple tricky aspects of it. It's not overly difficult, but there are a couple things that you have to be careful with. We'll review this question in our next session. Thanks again for listening. Hopefully you have no questions, but if you do, as always, feel free to contact me. Thank you again. Bye-bye.